What you just witnessed is what mathematicians call an attractor, an Aizawa attractor to be precise. And the equation of the Aizawa attractor consists of three differential equations. And differential equations are equations that determine how something changes over time. So for example, you have the differential equation for the x-axis, the y-axis or the z-axis. If you have the one for the x-axis, it tells you how does this point change over time over this x-axis. Or you can do it over the y-axis or you do it over the z-axis. And that way, if you combine those three things, then you're getting the determination or the calculation of the position of a point in 3D space. You also see the parameters A, B, C, D, E, F. And no worries, at the moment, we'll not talk about them yet. Later in this video, I will explain in detail what each of these parameters does. But for now, let's jump right into Blender to create this very cool abstract animation. So what we're going to start off with is going into geometry nodes. You can click on the cube and add in a new geometry nodes for it. You can remove the group input because we don't actually need the cube. But what we're going to start off with instead is a points node. And this point is what we want to give the equations that we saw earlier. So to get the movement for those simulations, we want to do Shift A and do a simulation zone. And we want to move our points. So let's do a set position node. Set that over here. And we also want to have an initial velocity or a initial position, so to say. So in the simulation input, we're going to press N and then you can click on plus over here to create a position attribute. And then the socket type is going to be vector, of course, because it has to be a 3D point in space. And now you can connect position with position and position with position over here in the set position, so that it will update over time and it also updates the point itself. In order to make the equations work on the point should not have an initial position that is 0, 0, 0. So what we're going to do is do a random value node set to a vector. And for now it's okay to keep it on 0 to 1. Later we will maybe change it. And let's connect this one with the position. And then in this one we can do a position node like this. Now every frame we want to update our position with the equations that I just showed you. So we're going to do this by adding in a vector math node. Keep this on add because we want to add the equations. And you see this vector value over here. This is the value for the x-axis, the y-axis and the z-axis. But right now you see we have it only as one socket. Right? I want to have control over the separate X, Y, and Z socket. And to do this, we do a combine X, Y, Z node and we connect it like this. And now we have separate sockets for the X, Y, and Z. So basically now we can recreate those equations for the X, Y, and Z with math nodes that come with Blender. Let's create the setup for that first. What we're going to need first to get those equations is a position node, because we need to have the current position of the point to calculate the next position. And from this position, I want to do separate X, Y, Z, so that we have separate values for the X, Y, and Z position. And then let's also do a Shift A frame. And this frame is just to organize things a little bit better, because now we can say, okay, in this frame are going to be the nodes for the dx dt equation. We of course also need the parameters that we saw. And to create the parameters, I think it would be good if we do a group input. And in this group input, we see, yeah, we have geometry, of course, but we can also give more inputs out of this group input, such as those parameters. So if you take the group input and you go into the group over here, and then you can click over here on the plus to add in a new input. And this input I'm going to call A. And then to add in the other ones, we can do plus to do B, C, D, E, F. Okay, so now let's rename them to B, C, and D, and E, and F. Now we have those inputs over here. And these inputs, you can find them over here in the geometry nodes as these values. We will not change these values yet. We will do that after we've inserted the equations. It's a little bit easier, so we don't have to worry about that now, but we just needed these to connect them with the right math nodes. So for the dx dt, you see we first have to do z minus b. So let's add in a math node, put that like this and set it on subtract. And then we can subtract z minus b. And to keep the overview a little bit better, I like to click on this math node and go into the node over here. And as the label, we can do z minus b. And then this, we have to multiply that by x. So let's take this one, Shift D to duplicate it, and let's rename it with an X behind it. And let's set this on multiply, and we have to multiply this by the value of X. Then we also have to create D times Y. So let's take this one, Shift D to duplicate it to here, and let's name this dy. And we have to multiply D with Y. And then this one, we have to subtract that from this one. So let's take this one, Shift D, and let's add to this label dy. Set this on subtract, and let's subtract from this one, subtract this one. And then this is the equation for dx dt. So we're going to connect this one as the x of the combined xyz. Make a little bit more space, like this. And this is basically what we're going to do for dy dt and also for dz dt. So if we take this whole thing and we press Shift D to duplicate it, we can now delete these parts and rename this dy dt. And then we can do that again. For dy dt, you will see that we have to start with multiplying d times x. So let's do a math node, set it on multiply and name this dx. And let's do x times d. You see, we also have to do again z minus b. So let's do another math node, set this from subtract and rename this to z minus b. And then let's connect z and b like this. You now see that we have to do this times y. So let's take this one, Shift D it, subtract to multiply, and let's add y to the label over here. And now we want to multiply this one with the y position of the point. And these two, we have to add those together. So if we take this one and Shift D it, we can rename this label by clicking over here, copy this one, Ctrl C, go to this one and do plus Ctrl V. And then you can set this on add and add these two together. And now we finished the dy dt formula. So this one is going to be updating our y-axis for the point. Now let's do the z coordinates. So let's take this part and Shift D it to here. We can delete these math nodes again and rename this to dz dt. And you see the z coordinates are a little bit of a bigger calculation. But no worries, what we're going to start with is a times z. So let's do a math node, set this to multiply, and let's do a times z. And let's rename this az. You also see that we have to add c to this. So let's take this one, Shift D it, and let's add c. So let's do c plus that. So let's now take the c, put it as the first one in the add, and add az to it. Now we have to take z to the power of 3 divided by 3. So let's do a math node so that we're first getting z to the power of 3. So let's set this from add to power and do exponent as 3. And let's plug in the z. And let's rename this to z to the power of 3. And now we want to divide this by 3. So let's take this, Shift D, set it on divide and type in over here, divided by 3. And let's take this one and divide it by 3. It's already on 3, so that's good. This one, we need to subtract that from this one. So let's take this one and press Shift D to duplicate it. Set this on subtract, and let's take this one and subtract this one from that. Let's also take this, Ctrl C, and do minus Ctrl V, so that we keep our overview. Now we need to create x to the power of 2 and y to the power of 2. So let's take this z value and let's press Shift D to duplicate it and name this x to the power of 2. Let's make the exponent 2, and then you can Shift D this and name this into y to the power of 2. Now you can connect x to this one and y to this one. And this we need to add to each other. So if we take this one, Shift D it, and then set it on add, we can add these two together and then make this x to the power of 2 plus y to the power of 2. Next part is going to be 1 plus ez. So let's first create the ez. Ez, we're going to create that by adding in a math node. Set that over here. Set it from add to multiply. Name this ez. Let's move this a little bit down. And let's take the e and multiply that with z. We have to add 1 to this. So let's take this one, Shift D, set it on add. Make the first value 1, and let's add ez to this. And let's name this 1 plus ez. Okay, this one and this one, we have to multiply that with each other. So let's take this one, Shift D it to here, set it on multiply, and let's multiply this one with this one. Now you can take this one, Ctrl C and Ctrl V. And then this whole thing, we have to subtract that from this one. So if we take this one, keep it on subtract and connect this one over here, and we want to subtract this one from it. Now you can take this, Ctrl C, and go over here and do minus Ctrl V. You want to see the whole thing, you can expand it by dragging it a little bit like this. Now we need to create the f, z, and x to the power of 3 part. So if we first take the x to the power of 3 by taking this z to the power of 3 and shift D it to here, then we can rename this to x to the power of 3. And then instead of z, we connect the x-axis to the base. Now let's multiply this with z. So let's take this one and set it on multiply and make it z x to the power of 3, and multiply this one with the z-axis like this. Now we want to multiply this with the value of f. So if we take this one, shift D, and we name this fz x to the power of 3, we can multiply this one with f. And then this whole part, we want to add that to this big unit over here. So we take the big unit and we press shift D to duplicate it. We set it on add, and we want to add from this one, we want to add this one. And then let's keep our overview, do Ctrl C over here, go over here, and do, in the end, do plus Ctrl V. And then you have the whole formula for the Z coordinates, and we can connect this into the Z axis like this. Okay, nice. Now we have our equations in Blender. That's good. Now let's take a look at what it looks like if we press play. You see, if you press play, the point kind of starts to do the spiral thing, right? However, it stops in the middle. That's because it goes way too fast right now. Let's slow it down a little bit by going in the simulation zone and add in a vector math node. Set it over here and set it from add to scale and set it on a scale on 0.01. And then you will see it will start going a lot slower. Yeah, and now you might be thinking, now it's not doing anything anymore, right? Well, you would think that, but it's just going very slow at the moment. But that's actually good. Because it goes very slow, it can very accurately calculate the Aizawa attractor. We just have to wait for a long time. So what we're going to do is the end frame of our animation, we're going to set that to a very high number, like 5,000 or something like that. And then we're just going to bake our simulation. So if you go over here into the physics, and then in the simulation nodes, you can do bake, and then it starts baking it very quickly, as you see. Let's wait a little bit until it's kind of like 3000 frames or something like that. And then we'll take a look at what it looks like. Okay, I know I said that I was baking the whole simulation, but after baking it, nothing really happened. And I was wondering, like, why it's not happening? Why is it not happening? And then I found out that I'm stupid. And that I didn't realize that we didn't put the right parameters yet for the A, B, C, D, E, F parameters. So I guess that's what we have to do first. On the internet, I found the right parameters for the classic Aizawa attractor. And we're going to fill them in now. For the A parameter, we're going to put 0.95. For the B, we're going to put 0.7. For the C value, we're going to put 0.6. For the D value, we're going to put 3.5. And for the E value, we're going to put 0.25. And then for the F value, we're going to put it as 0.1. And then you will see, if you press bake and you play it, then you will see your point will start moving really as the attractor. So what we want to do now is make this so that it's not one point, but that it's actually kind of drawing a 3D shape in space. And to do this, I want that this point leaves like a trail of points along the whole simulation. And to do this, add in another simulation zone. And on this simulation zone, we just want to do a join geometry. And then join the simulation output like this, so that every frame you're joining a new point to that group of points. And then if you connect that like this and you press bake again, then you will see we have this, which is pretty cool. However, I don't want this to be points. I actually want this to be one curve that creates this shape, right? So how do we convert these points into one curve? Well, we can do that by taking a curve line node. And this curve line node, we connect that like this, we see we have a curve line, right? Right now it consists of 2 points, over here and over here. I want that this consists of more points. So we do a resample curve node. Now it consists of 10 points. And these 10 points, they have an index, right? So index 0, index 1, index 2, index 3. These points that we had also have an index. They also go 0, 1, 2, 3, 4, 5, 6, 7 until the end. So we can say, for example, okay, the point on this curve with an index of 3 should get the same position as the point in this one with an index of 3. So we should link those together. And to do this, I want to have the position of each index of each point. So let's add in a sample index node, connect the geometry over here, set this from float to vector because we want to have a vector, the position, right? So let's add in position, we want to have that. And we also want to do index so that we have the indexes of the points. And now to make it that this curve follows these points, we want to do a set position and connect the curves with that. And then if you put the sample index into the position, now if you connect this like that, then you will see it will start working, but you will see a better result if you set the resample curve higher. Then you will see it will start working. And now to automate this a little bit, we want to make it that this count value is always the exact same number as the number of points that we have. And to get the maximum number of points, we can do an attribute statistic node and place this geometry into this geometry. And we want to use the index of the points because now we can determine what is the maximum index. So what is the maximum amount of points that we have? So if you now connect the maximum value into the count, then you will see the curved line starts growing automatically with the points. And if you bake the full 5000 frames, the longer you bake it, the cooler the results will be, of course. But now this is still just a curve. Let's give it some thickness so that we can actually render this out and give it a cool material or something like that. And to give it thickness, I would actually recommend to not do that within this geometry nodes. I would name this geometry nodes like the shape creator or something like that. And giving it actual geometry, I would do that in a different geometry nodes. So if we go into the modifier properties, and if we do add modifier, we can do geometry nodes to add in another one. And then if you click on new, you can name this make thicker or something like that. And we're going to do this pretty easily. Just do a curve to a mesh node. And as the profile curve, we do a curve circle like this. And let's give the curve circle a lower radius like 0.02. And then we're already getting this. Looks cool, looks pretty cool. However, over here, it's like a cut off, right? And I think it would be cooler if we can make it that it like becomes thinner in the ends. So that if you want to animate this, that it actually looks like the thing is growing. So to do this, let's add in a set curve radius and also a spline parameter node. Connect the vector with the radius, and then you see over here it is thinner than over here. But now it's only the beginning of the curve that becomes thinner. And this is seen as the end part of the curve. So I want to make it that the beginning and the end are thinner, and the middle is thicker. Do this by adding in a float curve node. Set that like this, make both parts 0, and then take the middle part and drag that up. So that over here we now have a part that kind of looks like it starts growing. Oh, and by the way, we can also set in the curve circle the resolution lower to like 8 or something like that. Do that because that will save you a lot of computer power. And the cool thing now is that if you take this one, for example, and you press Shift D to duplicate it, and you press right click to put it perfectly back, now we have a new one. But you see this new one is not there, right? That's because we have to bake it again. But before we bake the simulation again, I'm going to change a little bit of the parameters so that we have a new variation of Aizawa attractor. So what I will do is I will make this one 0.6, for example. I will make this one 6, for example, and this one 0.9. And now let's bake it again and let's see what happens. And then we're getting a completely new one. You now see that I've been changing those parameters, right? But what do they actually do? Let's start with the A parameter. The A parameter determines how narrow the attractor should be. So a higher A value results in a more narrow attractor, while a lower A value results in a wider attractor. The B value influences the twistiness of the attractor. So higher B values will lead to more twisting of the attractor, while lower B values lead to more smoothly going shapes. Then the C value determines how smooth the loops of the attractor go. Higher C values will make the loop larger, while lower ones will make the loop a little bit smaller. The D value kind of does the same thing as the A value, however it stretches the attractor in a vertical way, so it stretches it from top to bottom and not making it wider or something, it makes it longer. The E value pushes the attractor up or down. Higher E values result in a more upward attractor, and a lower E value makes it that the attractor is pushed a little bit more down. The F value is a little bit the same as the E value, only then it doesn't do it vertically but horizontally. So higher F values will shift it more to the right, while lower F values will shift it more to the left. Now that we've taken a look at the parameters, the last thing that I want to do for this video is showing you very quickly how to assign a material to this. So what you want to do is go into material preview mode and then split your screen like this to go into the shader editor. And let's see, we have the Aizawa material over here, and let's make this red, but you see nothing happens. That's because we have to assign that in geometry nodes. So in geometry nodes you can go into the modifier properties and you want to assign this material in the second geometry nodes that we've created. So in this make thicker geometry nodes, let's press Shift A and do a set material node, and let's set this on the Aizawa material. And then you can make it any material that you like. I like a more metallic look for this. If you want to animate it that it rotates infinitely, you can click on it and we can automate the Z rotation over here by doing #frame divided by 10. And then you will see it will start rotating like this. However, if you rotate it like this, then you'll see that's not really what you want, right? You want to keep it that it rotates along its own axis. So instead of rotating it manually, you can take the delta transforms over here. And then if you put the rotation, the Y rotation, for example, like this, then you will see it will keep its local Z rotation. And I think with that we have achieved something pretty cool. I hope I didn't scare you off with all the mathematics in this video, but if you actually liked the way how to combine mathematics with Blender, you can give this video a thumbs up, comment down below if you have any questions, and if you don't want to miss out on any future videos, I consider subscribing. And with that being said, I see you in the next one.